To help us think about the second half of the year, I thought at least one more time I would remind you about the first half of the year. We haven't had any pep rallies this year, so we haven't had a chance to actually do our calculus chant. So I figured we could try it in here one more time. So remember, when I say derivative, you say slope. Okay, make sure you understand that. Make sure you understand that the derivative of an equation gives you a slope formula, and of course you plug into that, and out pops the slope. So what's our little chant for the second half of the year? Well, it's not quite as good. I'll just let you know that. It's almost a little bit of a joke here, but instead of when I say derivative, when I say antiderivative, so it has an extra syllable in it already, but when I say antiderivative, you say not anti-slope. Okay, what would that be? I don't know, actually. What would an anti-slope be? But not bad. You're kind of thinking about the equation side of it, right? You can go up the ladder or down the ladder. This is a little bit more of a graphical chant, because when we think about the derivative, graphically we get the slope. You're getting warmer. You're kind of thinking about the application velocity to position. Okay, I'll be honest, I'm not sure there's a reason you would know this. The things that you guys are saying are true, depending on what function you start with. But here's kind of the big idea. Again, I don't know if there would be a reason you would know this. So when I say antiderivative, you say area. Really? Area? Well, yeah. It ends up being true that an antiderivative, in its essence, will help you to calculate an area under the curve. We call it area under the curve. That won't be the last time you hear that, but I also don't expect you to have it all figured out. But I do want to give a little bit of a, what's up with area? Like, why is that such an important idea? Okay, well, a little bit kind of like Aaron was saying, it will have a connection to position. And that is when we think of this as a little bit more of like as I call it up here, sort of the train problem. The stuff that you're seeing up here in this train problem is a velocity, and a time. Now, you can write this down if you want. I see some of you writing down. That's fine. That's why I gave it to you. It should be occurring to you at some point in the next 5 seconds that this is a really easy problem. Make sure that even if you're writing it down, that you're thinking. Because again, this is supposed to be a really easy problem. I want you, though, to be reminded that any distance, if I'm trying to find the total distance, but any distance, yes, just like you learned back in junior high or earlier, is always a rate and a time. And of course, that's exactly what we have for this train problem. It's not supposed to be a catch. I have a rate of 75. I have a time of 2. Sometimes it can be that easy. Of course, we went 150 miles. There's got to be a little bit more. There's got to be a little bit more. And there is. There's an area connection. Now, if we're going to think about area, we need to have a graph. You'll find out, because what we're really talking about is the area under a curve. So we need a graph. What I'm going to do is I'm going to suggest that we think about a physics velocity graph. Hope that that's not bad words to you. We'll kind of think about like a velocity graph. Let me help you just kind of get back to what I'm talking about here. When I say like a physics velocity graph, yes, we need like an x and y axis. It's almost always the case that the x-axis is time. In this case, the y-axis would be the velocity. Now this technically would be one of your easier velocity graphs because, well, the velocity is 75. So if we're going to draw a graph of 75, we would be drawing a horizontal line. And of course, that horizontal line is at a velocity value of 75. You can note that as the y-intercept. Just want to make sure that you get some bearings here. So we have 75. Also just kind of note that the velocity is 75. We got these times also. And basically 7 o'clock, 9 o'clock can find themselves on the x-axis. And here's where you should have a little bit of a aha moment. Maybe to my physics friends, you may have already talked about this a little bit in a previous class. But when I start to use my x values here as sort of boundaries, which can clearly make a space that has an area, we end up with a simple but pretty important observation. Okay, now the space that we're looking at here is like this rectangular region. Think about some of the things that are true about it. It's got a width of 2, if you want to call that the width. And of course, it's got a height of 75. I hope you realize that what I'm working towards here is the area of this space. But what it really represents is the area under the velocity curve. And so we're just trying to say area is important. Area is important because, yes, the area of under this curve is definitely length times width. It's 2 times 75. And of course, I know you saw that in a moment ago as the same thing as our distance traveled. Okay, so to sort of drive this home, the area, which is 150, does equal distance traveled. It does have some significant connection. It's more than just an area. Now, we will spend a lot of time thinking about this, but maybe you've kind of noticed that I'm starting with the velocity function. And Aaron kind of mentioned it, that if I do the antiderivative, I kind of go back up the ladder, then I should get to the position function. The position function being S for position, of course. But it's kind of like saying that I know the velocity, but if I know the velocity, I can turn that into a position or a distance. Of course, by using the area. Okay, so yes, there's a connection with the derivatives that we studied in the first half of the year, but now the arrow's pointing the other way. We're going back up, we're going back to distance. Now, even when I looked at it, it's kind of like, okay, that's nice, but I don't really need that, Miss Naylor. I can just do the basic math. And I agree with you. Until maybe we think about a more realistic situation where the velocity could vary. Now, if the velocity is going to vary, then the graph is going to vary. So let's one more time take a look at a velocity graph. I like this one. I hope that you like it too, because I'm trying to show you something a little more realistic, like if I had a velocity that changed. Okay, maybe my velocity went up for a while. Maybe it dipped back down. I slowed down. Maybe it kind of leveled off. Maybe my velocity varied. We'll just generically say it's a velocity graph. Here's what I hope that you still say. Here's what I hope that you still say. And it's our little chant, actually, because if I say well, antiderivative, which we didn't really talk about that here, but you still say area. There's still area under this graph. It's not a little rectangle, but there's still area. Now you guys will see areas eventually kind of in your sleep. It'll be one of the main things that we talk about for some time. It's not what we talk about for the whole rest of the year. But again, you will see areas. And notice, I said it kind of verbally, but just notice that it's always between the curve and the x-axis. So whenever the teacher says area under the curve, it always means to the x-axis. The x-axis is kind of like your assumed boundary line. More on that in some time. But why would this still equal distance traveled? You know, it's not a rectangle. Does it still actually equal distance? Well, if you think about it, you still have two dimensions. One of your dimensions is, let me back up a second. The area is still found by two dimensions. One of the dimensions is still the height. It's still the velocity. It's still miles per hour if we can just generically use that as an example. And then the second dimension is still time. It's still the width of that region. So it's miles per hour times hours. And this is one of your more basic factor label problems, but it's worth looking at what would happen every time you take miles per hour times hours. What I'm trying to say is it doesn't matter if it's a rectangle or if it's some curvy shape. Whenever I take these two dimensions, I'm still going to end up with distance. Obviously, it wouldn't have to just be miles. It gives us something to put our finger on. Okay, so the area under a velocity curve. It'll be a little statement that will go with us many times. The area under a velocity curve is always equal to distance traveled. The area under a velocity curve is always equal to distance traveled. It's a statement worth repeating. It always equals the distance traveled. Just kind of curious to my physics friends. Was this something that was discussed upstairs? That's good. Now the cool thing is downstairs we'll learn how to find those areas when they are functions, when they are curved lines. And as you can probably imagine, that has everything to do with an antiderivative, because an antiderivative is going to help us to basically go backwards, but also be able to calculate these areas. So eventually, calculus really exists for physics. It's not really a secret. I mean, physics was meant to be done with calculus. Some students get it before the other, but eventually, hopefully, you put it together if you're going to study that. Let's find some areas, and most of this we'll do after the break, but let's find some areas. I just kind of want to set this up, and then we can get rolling. We're going to do it of like just a parabola. The parabola is kind of the math teacher's go-to function. It's not too complicated, but it's not just a little old rectangle. It's a parabola. So we're going to find the area under y equals x squared from 0 to 6. We're going to find the area of y equals x squared from 0 to 6. And it would probably make sense to get a little visual. It's actually what we're going to have to do after the break. But let's just think about it a little bit right now. If I'm going to find the area of a parabola, like we said verbally, that means to the x-axis. And as I mentioned, soon you'll start to see areas, well, in your sleep, or just you'll start to see them. So when we say the area from 0 to 6, we are talking about a region. We're talking about a region that actually has a boundary. You see how I used the x values, especially x equals 6, but I technically used both x values to create this boundary. And so we're going to calculate we'll calculate that area. All right, it's a good stopping point. Get you to come back and